Hello everybody, good afternoon. Welcome to our talk. Just a short introduction. My name is Colin Malner and this is Matthias Neugeschwandner. We are both like postdocs at, I'm at a university in Boston and Matthias is in IBM research in Zurich. And we're going to talk a little bit about Windows security. But this talk is like obviously a defense talk. And we have been working in mitigation research for like the last couple of years and did like various things and for like mobile devices and for Windows. And today we're going to see what we did for Windows. So obviously software security is hard. Software has bugs and bugs are hard to fix, even if you even harder if you don't have source codes. And of course, bugs get exploited. And preventing this initial exploitation, just like getting, for example, PC control is like super hard. But in order for exploits or to like do anything useful, they need to have like a payload. And if the payload is very simple, then it's maybe just like a proof of concept. But if you actually want to do something useful, the payload has to be complex or more complex code. And our idea was, let's not go after all like this initial exploitation things. Let's go after this like more complex payload and make life for attackers like way harder by breaking payloads. So normally when you have like an exploit, you have like this like multiple stages, and in the initial stage you just like try to get program counter control. And once you have program counter control, you like direct it somewhere. Either you have like in the old days you have some code on the stack you introduce on the heap, or today you have like some rob chain. But you also have so even if you have a rob chain, normally you have like some payload. So what the attacker normally does, he like prepares like this like introduced code. And then just executes it. Like, of course, you can have like a completely rope-only payload, but yeah, the really like complex payloads are like unlikely to do that. And what the normal preparation is, you have like some code somewhere in memory, and you need to like make this like memory executable. What often happens is like that the attacker will just like load a DLL because the whole DLL loading mechanism just like sets like certain memory regions just to executable. And like of course exploit like payloads, they use like system functionality, and on Windows it's mostly functionality is like presented and DLLs loaded by like the target application. For example, like NT-DLL, kernel DLL. But of course the payload can also just like load additional like system libraries if to like add new functionality or functionality that the actual exploited application doesn't have. And in Windows, you normally use, you call system functionality via DLLs. You normally don't use directly call syscalls because like the syscall interface is unstable between like across different Windows versions and service packs, right? Yeah. So in the normal case, you have like your application. So this picture we will use like throughout this like presentation. So this is. So you have some application, you have your DLL, and then at some point the attacker, for example, loads like his own DLL into the process, either from like a local drive or from a network drive, and then has like his code running in the application. And here we looked at some Windows APIs that are used by my Metasploit. Do you want to like say a few words about this?
Yeah, so we just took a look at a couple of Metasploit payloads and checked which kind of functionality they actually use from very common DLLs. As you can see here, for example, second from the top, load library is usually used to load like additional payloads, load additional DLLs, or then you have like almost all of them use virtual alloc to, for example, allocate additional executable space. So this is like typical functionality. It's and then there's a bunch of network stuff as well from WinInit or WinSock too.
So, but we obviously are not the first to like look into like hardening applications, and like the most like relevant, I would say, work in like previous work is like this EMET package from Microsoft, And it's basically a DLL that gets injected into processes, and this DLL then will, like, for example, prevent setting the stack or heap memory executable. It will prevent like loading DLLs over like network drives, and really a bunch of other things. And EMET is basically, it's a DLL that just gets injected by the Windows framework, and it hooks some APIs and user space to like enforce all of this like features. And our idea was like, let's build something similar to EMET, or like follow along in this path. We have like some hardening that we add in user space into the application process itself. So basically, what we really want to do is, break the payload. So payloads, as I said before, needs some specific functionality, and this functionality is basically it needs to call API, like specific APIs. All the functionalities that's used by this payload might or might not be used by the target application. But as soon as like a library is loaded into a memory of a process, every functionality, if it's used by the application or not, is just there for the payload, for the exploit, for the attacker to like freely use as he wants. And our really main idea of this project was, let's remove functionality that is not used by the application, but still in the process of the memory. Very, very simple example. You have some server application, and the server might use for functions like socket, bind, listen to accept like new connections and handle them. But the server application might not use like connect, because it like never connects out. So if we remove connect from that process, if you have, for example, some exploit, and the exploit tries to like do a back connect, there is no connect functionality anymore in this process, and so like this like very basic way for like the attacker to like get a connection backward to like his like control server cannot be done anymore. And this says, hey, if we can do this in very universal, remove like unused functionality, we should have like a really cool security improvement in general. So then we thought, hey, it would be really cool if we like can remove stuff like process creation, library loading, networking from applications that actually don't use it. To really reduce like the attack surface that is present. And now I'm gonna give it to
So if we take a look at modern software today and like wrap things up from the beginning, so you have applications that actually rely on shared code, because right as a developer you don't want to reinvent the wheel, so you want to have some GUI functionality, then you use pre-existing code. And that code usually comes in the form of a dynamic link library, which is basically a binary file that gets linked into the at process startup, the DLL together with the main exe of the program gets loaded into the process space. So that's where we basically hook in our solution. And the operating system itself provides a couple of basic DLLs. And also another advantage is that DLLs can be updated independent from the app. So say, I know you have some new code that displays stuff, then this is automatically going to be used. So when we initially thought about the project, we thought that, okay, there's one app and it's going to use like a couple of basic system DLLs like NTDLL and kernel 32 and a couple of other libraries. And actually you're going to see that slide. We're going to refer that more often. But it turned out that we weren't exactly right, because we vastly underestimated the number of DLLs that are actually being used by an app. Because if you look at modern software, it really looks more like this. Modern software has, modern applications link up to like, DLLs in the number of hundreds. So plus 100 DLLs is actually not unusual for a modern application. And even if the application will just use one function of a DLL, so one function that's being exported, it still has to load the whole DLL and all the code that comes with it. And the process actually also has access to all the code of the DLL that it might not even use. And as an example, we actually took a look at Adobe Reader, and we started out with the DLL that provides like the main functionality of Adobe Reader, which is at read32.dll. And then we looked, okay, what are the dependencies of this DLL? And okay, it was already a bunch. But then again, you have to think that's just the initial step, right? Because these DLLs themselves, again, depend on other DLLs. So that was the next step. And then these DLLs depend on others, and this goes on and on and on. And in the end, you end up with, yeah, over 100 DLLs. And this was just using static analysis, so the actual number is even higher. On the contrary, when you look at what Adobe Reader actually uses out of these DLLs, the picture looks quite different. So on the top here, you have the exported function usage that will actually show you in blue, okay, how many exports are there per DLL, and then in red, how many of these functions are actually being used by Adobe Reader. And you can see here that it's usually, okay, 1/4 at maximum. And even below, the second graph shows you, okay, the code that is actually, that implements this functionality. And of course, because of some overlap, there's actually more code being used, but still it's like the maximum is half of the code of NTDLL, for example. And good example here is WinSock again, because Adobe Reader just uses 1 or 2 functions, I think, out of WinSock. And so the code usage here is really, really, really small. And this is not only true for Adobe Reader, actually, we also took a look at another app that's Viber. It's a messaging app. It's a messenger. And here you can see that, okay, you have like a slight increase in the usage of functions for WinSock, of course, because it's, yeah, well, it's messengers, it uses network functionality a lot. And it's also reflected by the code usage, but still the picture in general is similar. So there's lots of potential for actual removing unused code.
So yeah, so now we talk a little bit about what is the problem, what do we want to do. We saw that there is like potential for like removing code, and so we came up with like the system which we like named code freeze. We have like 2 big components in here. One is like the dynamic code stripping, and you have the second component we call image freezing. So the code stripping really is removing the unused code from the process. And I say process here, not application, because we do everything on the fly in memory only, so we don't modify anything in the application on disk or in the DLLs. And specifically what we mean by removing code, we mean removing code from DLL code only. So we don't analyze the actual main application, but we really only look at system DLL code. And image freezing basically is the idea that we want to prevent loading new code into the processor's address space. Specifically, what we actually do, we just prevent creating new executable pages, which also prevents, for example, code injection via library loading. And as I said before, we do all of this at runtime, so there's no modification of anything on this applications at all. So if you want to remove code that is not used, we first have to like find out what code is actually used by an application. Application or PE files, so basically they have like an import table. You say we use like this function from this library and this function from this library. And obviously DLLs have like export tables where they say I have this function at this address in the file. And if you really basically look at the basic thing, we say, okay, unused code is functionality that is not imported by the main executable file. But of course, there's dynamic function lookup like get proc address and so, and yeah, we will talk a little bit about this later. But just to get the idea, yeah, exports versus imports, the stuff that's not imported can be considered not being used. And to actually determine what parts yeah, of the code use other parts, we look at the program's control flow graph. So we split up a program into like code blocks and branches and jumps between them. So we have some basic blocks, which is like a node in our CFG, and then we have in the edges are the control flow transfers. So basically, yeah. So we have like this nice like graph view of like each DLL. That's what you're gonna look at. Yeah, this is like our main picture. So we have this like the application, and it has a bunch of DLLs. And then, so we generated this control flow graphs, which we will talk about a little bit later. So basically, for each DLL an application uses, we pre-generated these control flow graphs. So there's like gray bubbles in the beginning, and those are like the program exports, and like the other nodes are like other parts of the code that are used by these exports. And in this DLL, this control flow graphs of the DLL, they're independent from the application. It's just like, for example, we generate this for like NT DLL, kernel DLL, and so forth. So we have, this part has to be done only once. Then, as soon as our tool executes, we look at the DLL exports and really just go through the application import table and mark all the different nodes and functions within the control flow graphs if they're used. So all those blue nodes are like represent code parts of a DLL that are actually used by this specific application. And since we now know what is used, we also know what is not used, like everything that's still white and gray, this is not used. And this is information we can go to the library code in memory and start deleting or removing that unused code.
Yeah, so since we work with binaries, the very first step that we need to do is like control flow recovery. And what we do for that is we basically use recursive disassembly. So we start disassembly at the entry points, and then we just follow all the control flow transfers and resolve them, split out in basic blocks and so on. And this is actually not a problem at all, as long as you have direct control flow transfers. So as long as you know which address, as long as the address is actually in the code, so we know where to follow. Well, this doesn't work that well, this with indirect control flow transfers. So here on the left-hand side in this basic block, there's actually a memory address being loaded from the memory into a register, and then we jump to that to the address that is stored in that register. And of course, with static analysis, offline we don't know where this is actually going to point to. That's an indirect control flow transfer, and that can be troublesome. Reasons for indirect control flow transfers are manifold. One things are jump tables, where you basically have that are generated when you have switch statements, where you have tables in memory with all the addresses. Then there are callbacks. So say you just want to register a callback with the DLL, then you have a function pointer therein that's going to be used and being only determinable at runtime. Another thing are virtual function calls, if they're implemented via vtables for object-oriented C++ code. And then, of course, dynamic code loading, where you use functionality like getProc address to resolve the function address at runtime. However, for the like internal cases, abstract interpretation can help. Abstract interpretation is one of those nifty static program analysis techniques that use data flow analysis. And in this case, what we use is bounded address tracking, so the basic idea is that you are able to determine like the values of variables, like this register, based on a very low-level memory model, and using solely static analysis, so not actually executing the program. And so our whole setup for control flow graph recovery that we have is, so we set out with IDA, of course, what else? It's basically state-of-the-art, industry-grade recursive disassembly, and also does already some basic control flow recovery. Then we use Checkstep. Checkstep is really it's an academic abstract interpretation framework, but it's really usable. So if you do program analysis, you need a data flow or abstract interpretation framework. Check it out. It's a Java program, and you can really use it. So it's not like one of those academic prototypes that are more difficult to use. And it gives you back basically a listing of the assembly with the targets resolved if it manages to. And basically, so we use the output of those two together, and then we have Python glue code that pieces all the different stuff together and also processes stuff like imports, exports, and then the API sets that have been introduced with Windows 8 and so on. And the result of that are our kill files. Kill files actually contain the input that we use during the runtime code stripping. And what they basically contain is a call graph of the DLL. And the nodes within those kill files are functions plus the internal dependencies, so the code regions and the external dependencies. So functions that are imported by the DLL from other DLLs. And this is what such a kill node within such a kill file looks like. So we have process 32 next here. That's the function, that's the export of this DLL. The DLL is count 32. And then we see at the top, we see the code regions within the DLL that this function uses, so that we know exactly, okay, this is the parts that we can strip or that we don't strip. And then below that, you see the external dependencies that we have. So, for example, this process 32 depends in NTDLL on NTMap view of section. Then we also have a second example here. So this is from WinSock. This is the networking API of Windows. We have duplicate socket A, and we only have a small code region here. And what we do also have in this case here is internal references. So if there's a sub-function used within the DLL, we also list it here so that we can refer to it. One thing that happens when we cannot resolve an indirect control flow transfer are orphans. What are orphans? Well, we named orphans internal functions that are not being exported, so they are not entry points of a DLL, but they are not referenced from any parts of our internal CFG. And they are troublesome because we need to whitelist and to enable their functionality and also the external dependencies. Because we just don't know whether they're actually being used or not. This is due to the imperfection of the CFG. So we need to whitelist them during runtime. Okay.
So now we told you a little bit about like the idea, some more details. I'm gonna present you our actual implementation, and we're also gonna show you some demos. So the basic implementation is the enforcement module. This is a DLL that is injected into the process, very similar to emit. And what our DLL actually does, once it gets loaded, it actually patches the program's main entry point so that our code executes before the application ever executes. So we can do all our operations. And then at the end, we can just let the program execute normally. Our proof of concept we implemented for Windows 8.1 and 32-bit mode. I am not that experienced with x86 or Windows, so for me the 32-bit stuff was just easier. But there's no reason why this doesn't work on 64-bit implementations. We just the demo is for 32-bit mode. Yeah, so just a few words about DLL injection. Either we use app in a DLL, which is a user32 functionality, so you can just set something in the registry and we get our DLL injected. But we can also use this Q user APC where we can just inject code into any application. Depending on what the application uses, we can use either. It doesn't really matter. So before actually you can run an application with the code freeze and enforcement mode, you have to run the application with what we call the code freeze monitor. Basically, it's another DLL that we inject into the program, and then which collects DLL names of DLLs that are dynamically loaded. It will find all the functions that are used via get proc address. And it will also check if the application ever allocates memory pages that are executable or changes some pages. So basically any modification of executable memory pages. And after the end of this monitor run, this generates a configuration for the application, basically a list of DLLs that needs to be preloaded, and a list of functions that are going to be whitelisted. For example, every function that's called via get proc address needs to be whitelisted, and the settings for the memory permission enforcement. A few words. Why do we have to do DLL preloading? We have to do preloading in order to be able to strip code from dynamically loaded DLLs. So if a DLL is loaded only further in the program, we cannot do our enforcement anymore because we do enforcement only at program startup. So that's why we do the preloading. And preloading is really we just load every application, every DLL. Using load library, and then we can do all our operations on that DLL. And as soon as the actual application calls load library, the load library call will just return the handle to the previously loaded, like to the library since it's already loaded. Very, very basic OS functionality. So how do we actually do code stripping? So basically we want to remove code from the process memory, and with remove we really say just make it unusable so that you cannot call that code anymore. For this implementation, remove really means overwrite the code in memory, and we'll discuss later why we are overwriting it. So then we thought, okay, what should we overwrite the code with? We could, like, for example, put a handler there, so it will just like jump to like some code from us, and we could show a pop-up and say, hey, this code should not have been called. But we could also like overwrite it with like some other stuff like zeros or like knobs or halt. Halt is like very interesting. I don't know if you watch this like TV show, which is on lately. Halt is basically like it's a privileged instruction on x86. So if a user space application calls it, it will basically kill the process or like trap a debugger. And the nice part about this is like a single byte instruction, so we can just like use memset on arbitrary address ranges. So we don't care how many bytes we overwrite. We can just like wipe the memory with this halt instruction. So about image freezing, so as I said before, the idea is we want to prevent the process from adding code to its like address space, but essentially it's just like preventing on setting page exec on a memory page. That's all that is the process. And if we do that, we can basically prevent code injection and library loading. So yeah, some sources of like page exec is of course if you either map a file to memory with like ZV create section, or if you like allocate memory, and of course you can also like change like memory protections with other functionality. So what we basically do is right now we hook those functions in user space, and with this we can selectively call switch off certain functionality. For example, you can say this application cannot like create more like file mappings where we get executable pages. This like userland hooking is really just for our prototype. We wanted to determine if we crash an application or make it unusable if we like prevent it from actually creating executable code pages. In a real world application of this prototype, you would have this enforcement part in the kernel where you can just say from now on, this process cannot like create pages with executable bits anymore. But this was really good, like in the user space hook was really good to just see if this will actually work and do stuff. A little bit earlier we talked about dynamic function lookup with but there's like other problems why we have to like do whitelisting of functions. So static analysis in modern software is not sufficient anymore. So sometimes you have to like kind of learn what function an application is actually using. So what we have is like special modes where we basically run an application with code freeze enforcement turned on, and then we have like a small script which like actually interacts with those applications to like cover as much functionality as possible. And if during this normal execution, like in like our test environment, if we like trigger like a crash due to a halt instruction, we could like then automatically whitelist and restart this testing. And we have like this fully automated like thing where you just like run an application in like a sandbox, or not a sandbox, but just on a VM where you do like automatic generation of this whitelisting. It's like just like two screenshots where like two Windows VMs running Adobe Reader in this to like test it out with this function enabled. So before I'm going to show you some demo, I'm just going to quickly step through what actually happens when an application is under code freeze protection. So what happens at code freeze in runtime? So you have this application, if you to the picture in the beginning. The application starts, the linker loader loads like all the DLLs that are referenced in the PE file. Then the code freeze DLL gets injected, and yeah, it will hook the application's entry point. And as soon as the code freeze is actually executed from the program's entry point, we start with DLL preloading. So we load all the DLLs that this application will need. Then we run the code stripping. So we use the control flow graphs to override memories with halt, override instruction in the memory with halt. Then we place the hooks, the API hooks that will remove the executable bit from whatever memory allocation or permission API is used, and then we just let the application execute its normal entry point, and from there on we could even unload our library. In this case, in our prototype we couldn't do that because we still have this userland hooking. But if the userland hooking for the page protection would be moved to the kernel, we could now just unload our DLL, and the application would just run normally. It's just some code removed. So I wrote this very small demo server just to show what happens during exploitation of an application that is protected by code freeze. And since I'm not a super duper exploit writer for Windows, I really wrote a very simple program, turned off dep and ASLR, which doesn't have any effect on our code freeze system, but just saves me a lot of hours to basically create a demonstration for you guys. So. Okay. Let's start the demo. So just start this demo server. Let's go to the Internet Explorer. Just run some. We had some problems with Internet Explorer, but
yes, it's basically retrieving the website from the website.
Just basically here this page kind of works, but yeah, works. So we have this really tiny. So now we go to our tool. It's just a small Python script which just exploits the server, and as you can see, so.
Okay, so the exploit just launched the calculator.
Yeah, so you see there's splits it out. And now, before we relaunch the web server, or mini web server, we're gonna activate our system. In this case, we just use a registry. So you have this here, or our DLL, just going to be injected under here. We're just flipping the 0 to a 1. The protection, our system is activated. Now we just go and restart the web server. And I'm going to try to exploit our web server again. As you can see,
we're now trapped into the debugger.
Yeah, we're now trapped into debugger, and you can see instead of popping the calculator, the execution stopped because while trying to call winexec, it trapped on halt. So basically. And as you can see, if you just do a view memory at the current address, which would be winexec, you just see the whole memory is wiped with halt instructions.
Because winexec is just not used by the processing.
Yeah. So it's very. And now I'm just going to do a small just walkthrough. And I'm going to show you some of the where our stuff is stored. So we have here just right now it's just we say, okay, these two files are getting enforcement. This is just the list of just the directory where we keep all the control flow graphs.
Yeah, so it's basically the configuration, the control flow graphs, the kill files per DLL.
Yeah, for each of those is So if you just like check one of those out, and if you see, so it's like,
and this is an actual.
Yeah, that's a very simple text file for. Yeah, what else do we have? Yeah, and for example, like even this small web server had to like load all those DLLs. Yeah, that's it for this demo. Okay. Yeah. So some data. So this really small web server used a total of 15 DLLs, which is roughly 32,000 functions. And bytes, that's really just the raw instruction bytes. It's not the size of the actual DLLs, but it's just like the pure instructions that are in those DLLs. So if, for example, if you have a function, there's like some, in kernel DLL, for example, you have some bytes in between different functions, that's all not counted. These bytes are really the raw instruction bytes. And below we have the list of, or like the stats of like what did we strip. And in this case we strip like 3.4 megabytes, which is in this case 57% of all the code that we like stripped from the DLLs that are loaded into this application. And just like an overview of like some of the more interesting functions that were stripped that you see on top is like winexec and other process creation functionality. Yeah, so yeah, there's a bunch of other stuff, but it's like the more interesting functionality that is stripped. For example, our web server only like doesn't write a log file, so obviously something like create file is not there anymore. Yeah, and at this point, our system has like one smaller drawback, because we basically kill on-demand paging. So if you, for example, if you load a library and only use like 5% of the code, only this 5% of the code actually mapped into the address space. The other stuff is still there. So if you jump to a specific function, it will be just loaded by the OS. But in our case, we really have to load everything. So the memory footprint of the application with our proof of concept right now gets a little bit higher. But we have some ideas about how to fix this. So then it's like, okay, like a demo application is good, but we wanted to look at some like real world application, and Adobe Reader is like fairly popular. It is like really known for this like high quality, and there's like never any bugs in this application. So we just said, hey, let's see what we can do here. And in this case, like if we after testing Adobe Reader with like a bunch of different PDFs that have like different functionality, we actually managed to blow up Adobe Reader to like actually load 185 DLLs. 20 of those are like Adobe DLLs, so that's non-system DLLs, but the rest is like really 165 Windows system DLLs. In this case, we only do stripping, code stripping on system DLLs. So we say, okay, if an application brings its own DLL, we just assume it will use everything, and it makes our task much easier if we just like do stripping on Windows, on like system DLLs, because we can pre-compute all those control flow graphs, and if you install a new application, you don't have to actually like analyze whatever they brought. So sometimes this like video will like be a little bit slow because I recorded it on a VM on a different continent over the internet. I just like had some VM service. So maybe I should start it again. So we start again. Like the code freeze is not activated right now. So just to get a feel for like the speed of everything. So we just started Adobe Reader, and you can see the memory, the standard memory footprint. And there's like some additional going. So we just like open any any PDF. This is just like just to see, okay, this is like just a normal Adobe Reader and how fast things are without our enforcement. Yeah. And like just to look at the memory footprint,
which is a little bit larger now because the PDF has been loaded.
Yeah, yeah. And so now we go back and go to the registry, activate our system. I know, yeah. So this is just like this artifact is really just like network recording it on a VM over the network. So now we start Adobe Reader. Now we have like the full enforcement on, and you see it will take a few seconds longer. But this is really it's the only like speed reduction is only at when you like start the application for the first time. And now you see like there's now Adobe Reader by default uses a lot of memory because we preloaded like all those 185 DLLs. So, but now Adobe like decides so like so small like delay on application startup, the reader runs with full native performance. So if you just go and open a file, it's just as completely as before. Yeah, so all the like the slow scrolling, that's just like due to like recording it on a VM far away. So even if you just like open the second document, there will be no
there's really no slowdown
during runtime. And this document is like 60 megabytes in size. So yeah, now if you look at just take a brief look at the memory footprint again. Yeah, now you see there's a lot of memory used, but yeah, as soon as we start closing documents, it will obviously be reduced again. Yeah. So yeah, so if you look at some stats for Reader, yeah, so here we say 165 because we don't do enforcement on the Adobe Reader, like on their own DLLs. And this is just like a lot of code, 21 megabytes of pure instructions. I think it's quite a lot. And in this case, you still are able to like strip 28%. I think it's actually 28.9, but say 28% of code from Adobe Reader. And like some of the interesting stuff that gets stripped is like create process or accept. Yeah, this is like some of the more interesting functionality that is stripped. Yeah, so some advantages what we I think are really advantages of our system is that our code actually just runs before the actual application executes. So we actually do not like add like new stuff to the application code base. And in theory, and I bet also like 99% in practice, I bet. So if you actually have a bug like in our enforcement module, it cannot really be exploited since none of our code is like actually running during the application runtime. We execute with the application's privileges, so we don't like raise any privileges for our code, and we really don't induce any runtime overhead. We have this small performance hit when you start the application for the first time, and it takes a little bit longer. But if you think about server applications or long-running processes, this like doesn't matter at all.
Yeah, one of the big limitations is that we have right now, because we operate in binaries, is the quality of our control flow graphs. It's just because control flow graph recovery is really hard, and we need like almost perfect control flow graphs to do proper stripping. And as far as memory usage is concerned.
Oh yeah. So one idea was when we said, okay, how do we actually remove code? One idea was, hey, we could just like unmap certain parts of the library that is not used, but actually Windows does not support partial unmapping of files. So you cannot like map like a 10 megabyte file and then unmap like 2 megabytes somewhere in the middle. That's just like not supported. But if we had this functionality, you could just like, instead of overwriting the code, you can just like unmap that unused regions, and with that we also wouldn't have any memory overhead, because we wouldn't mess with the on-demand paging.
Yeah, and actually, so future work that we thought about is also like working at the compiler side a little bit more, because CFG recovery sucks. And one idea that we had is, because we're using lots of system DLLs, that actually when compiling those system DLLs, it would be nice if the compiler would just give us the CFG right away, because then we would get the perfect CFGs to begin with, and we wouldn't need to like have all this hard task of starting to recover them. Of course, this would, in theory, require access to the source of Windows DLLs, which is probably not going to happen. But one thing that Microsoft could do is, I mean, they could just provide us with just the CFGs themselves. So if we would have just this information, it would already be great to do code stripping. Yeah. So there's also one compiler thing that could be done. So the compiler could already group code and functions inside the DLL at compile time. So the code blocks that belong to the same call chain are next to each other. And then we would have more continuous blocks of code that we could strip, or that maybe in the future, if we at some point have partial unmapping, could easier unmap.
Also, if we also the group code together, we can also make sure like code will be like on start or end on page boundaries, because then we can really just like also use just like change, instead of like overwriting or unmapping, and just like change the protection for this page, so just be not executable. So yeah, there's like multiple ideas what you can actually do to like the system DLLs to like even improve our system, more, without like actually changing the actual applications that like sit on top. We're like at the end. We also only have like 2 more minutes, so quick conclusions. I think we wanted to like show you like a bunch of different things. Like one part was like, hey, applications actually contain a large amount of unused code, and this code is like available to the attacker. If we can remove the code, then we can like nicely improve the security of applications. And I think we have a good demonstrate fairly well that like our idea about code freeze, but stripping and unused code works at runtime. We don't need to modify any applications or actually like libraries on the disk. We don't have actual runtime overhead. We could make it work on like real world applications like Adobe Reader. We're gonna, on this URL, is like, this is not really live right now, but we will like release updated slides and some other information there. Yeah, thank you everybody. And if you have questions. The what? We have not looked into that, but that's a good hint. Yeah.
Since you're doing only static analysis, how do you know for sure that code is dead or not?
So we also have like this phase where we actually execute the application.
But you can't execute all the paths, right?
Yeah, but it works like sufficiently. I mean, of course, that's one of the drawbacks, right? Because we don't have those perfect CFGs. And that's why for now we also execute the application scripted, fully automatic, and
so you might crash an application, for example.
In the beginning, like that, yeah. So we have this like automated thing which we like run for hours and hours to like try to like for example, on video, just like open different PDFs, scroll, go to the different, basically try to execute as much code as possible to like weed out stuff we cannot find statically. But you're absolutely right. Like for many applications, you have to do this. For other applications, we don't have to do it like that much. But yeah. Oh yeah, so what we will basically do, we have we can say like this application can, for example, allocate execute like pages with executable bits, and then just support JIT. Of course, if an application supports like JIT, we can't like provide us like much add-on security as for an application without JIT. Yeah, but yeah, yeah, I guess we have to get off stage.
Thank you.
So, thank you, everybody.